If you don't know me, I worked on JVMs for a very long time, probably more than 15 years now. And all this time, I worked on something called JIT compilers. So I'm going to ask you a bunch of questions today. Who knows what a JIT compiler is? A few people. People know what the JVM is, right? I don't have to ask that, yeah. So Hotspot is the JVM of OpenJDK. And a JIT compiler, basically the way a JVM executes code, Java bytecode, right? It could be any source language, could be Java, Scala, or Kotlin, or Clojure, or whatever. The Java bytecode, first it's interpreted, and the interpretation is very slow. And then we compile the Java bytecode into native code on the fly while we are running the application, and that's called just-in-time compilation. And that's the opposite of AOT compilation. AOT is ahead of time compilation. That would be something like GCC, right, where you compile your C++ into a native executable. The JVM does it on the fly. So I'm a JIT compiler expert. Well, expert. I used to work for Sun Microsystems Oracle, so I worked on the JDK. I wrote a lot of the things that you're using every day. I hope at least you do. Then these are the three biggest projects that I worked on during my time at Sun and Oracle. So I worked on JSR 292. You might have heard this, Invoke Dynamics, support for dynamic languages. So there were two implementations of JSR 292. The first one was a lot of handwritten assembly code, like lots and lots of assembly code. The problem with that was it's very hard to maintain, and then the JVM runs on multiple architectures, so we had to port the handwritten assembly code to all the architectures that we supported, so a major pain in the ass. And then on top of it, we had a performance issue. So at some point, we hit a performance cliff, and performance went down like crazy. So we decided to re-implement this whole thing and moved all that handwritten assembly logic into Java, into a package called Java Lang Invoke. You might know that one. A lot of the code of Java Lang Invoke I wrote. So if it doesn't work, you could technically blame me. But I like to say the code that I wrote was perfectly fine, and after I left Oracle, other people broke it. So that's how I see it. Then I worked on something called Java Level JVM Compiler Interface, JEP 243, also JVMCI. So do people know what Graal is? Yes? A lot of people, well, actually not that many. Okay, I was wondering, you guys probably heard of Graal VM, maybe? So Graal VM is an umbrella term for basically three different technologies. Okay, one is, I'm supposed now to call it Graal VM compiler, but it's basically, it used to be called back in the day Graal. That was the JIT compiler, right? So that's one part of the whole piece. Then there is something called Truffle. Truffle is a framework to implement language runtimes. And the third piece is Substrate VM. And Substrate VM you might know under the name of native image. So these three things. And Graal, the JIT compiler, is written in Java, while Hotspot is written in C++. So there has to be an interface between the two so that C++ can talk to Java and vice versa. So basically what we did in JDK 9 was we took that interface, extracted it out of the Graal project, and put it in a Java 9 module. And we call it JVMCI, so that we can plug in an external JIT compiler on the side. And since 9, we have this interface, and it's rather stable-ish. It's not a supported interface, but it doesn't change a lot. So if you have OpenJDK 9, 10, 11, 12, 13, or whatever, you can use the same Graal jar file and use it with that JDK. That was the idea behind it. And one of the reasons we did 243 was for JEP 295. We also did that in JDK 9. It's ahead of time compilation. It's not native image, right? Native image is something different. The main difference between this and native image is that native image does not support the Java specification, while this does, right? So native image is a subset of Java, and this supports the full specification. The way this works, it's basically a small command line utility. You pass in class files or jar files or module names, and then it takes all the methods that it finds in the Java classes and compiles it with Graal, and then spits out a shared library at the other end. And then Hotspot can pick up these shared libraries and if you have a very big application that runs a lot of code when you start up, this might help you with startup. But it's very tricky to actually make it faster because of the dynamic nature of Java. All right, I now work at Twitter, best company on the planet. And this is what Twitter looks like. So we have hundreds and hundreds of microservices, and we have thousands of instances running of these microservices. And this is from 2016, so it's probably more today. And then on top of it, we run on heterogeneous hardware. So we, Twitter, we own our own hardware. We have our own data centers. We don't run in the Google Cloud or Amazon or whatever. It's also when Facebook and Instagram and Snapchat are down because Google Cloud is down, right? Then everyone comes to Twitter and complains about it because we are up. That's why, because we own our own stuff. One of the issues with performance optimization is hand tuning doesn't scale, right? I hope every one of you has at least tuned for performance once in his life, but the way it usually works is you sit at work at your desk and you're annoyed by the performance of something, right? And then you say, okay, I'll invest a little bit of time and tune it a bit. And this happens every 3 years, 5 years, never, right? So you can only, if you decide to tune it, you can only do a few parameters, right? Because you have to build up a model in your head to understand if I tweak that parameter in this direction, what's going to happen to performance, right? So you can only handle 2 or 3 or 4 if you're really good. And then it's very time consuming and error prone. And this, the last point is the important one. Upgrades makes optimality fleeting. So it's very important in today's world where agile is the cool new hip thing. Everyone deploys a million times a day because it's the hip thing to do. Even we at Twitter deploy some of our services multiple times a week. So the problem is the code you're tuning today, the code you're tuning for today will be different tomorrow because your code is constantly changing. And that means that many services operate below optimality. It's just the case, and it's the same at Twitter, right? Everything that we run today does not run at its best performance as it could be. But we don't know how much we could improve, right? We don't. So a little theoretical part of what performance tuning is. So we have a function f defined over domain x, and what we want to do is we want to find a configuration A that maximizes f, right? Whatever your f is. Could be throughput, could be reduced memory consumption, could be reduced CPU utilization, reduced latency, it could be anything. And very important, it's always subject to some constraints, right? And the most important constraint is it still has to work. You can actually tune too far so that it doesn't work anymore. And you will see later in the experiments that I did with our Twitter services that that actually happens. So this is performance tuning. If you've done it, you know how this works. So you pick a parameter, or a few, and then you run it with the thing you want to tune. You measure your f, and then you get your f back, and then you, a performance engineer, a highly paid individual, has to decide, is what I just got back, is f better than before or not? And based on that, you were tweaking your parameters. So what we want to do is replace that engineer, because you have better things to do, I hope, with a black box. And that could be anything, right? I don't care what the black box is and what it does, as long as it tells me which parameter value to try next. That's all. And we at Twitter, for this black box, we use something called Bayesian optimization. So a bunch of people might have heard Bayesian optimization before. It's been around for a very, very long time. It's nothing new. We're not inventing anything new here. We're just reusing something that's been around for a while. So it's a method to learn potentially noisy, that's important, objective functions iteratively efficiently. So because if we are tuning for performance, as I said earlier, today, and then the code is different next week, we need an answer quickly, right? We can't run these experiments for months because then the code has changed so much that the result we have, it doesn't matter anymore. So it finds new optimum a few iterations and works well with nonlinear multimodal. The high-dimensional function one is the important one, because if you pick, or if you take the JVM, the JVM has hundreds of parameters you could tune, right? So it's important to have a method then that can handle a lot of parameters. Sometimes I get asked, at one time when I gave this presentation, someone in the audience asked me, could I tune my database? Of course you can, right? You can tune anything you want that takes in parameters that will affect performance. You can even tune your Minecraft if you want to. I don't know if that makes sense, probably not. So if you want to learn more about the Bayesian optimization part and how this all works and the mathematics behind it, you should watch maybe both of them talks by my colleague Romke. He's the expert, he knows everything. He has a very soothing voice, much nicer than mine. So watch these YouTube recordings. The only thing I did, if you look at the slides that he's using, right, the only thing I did for my presentation is I stole his slides. So I'm going to walk you quickly through how Bayesian optimization works so that you will understand the data and the graphs you see later a little bit better. So we have a parameter that affects performance, goes from -6 to 6, and then on the y-axis we have performance and highest beta. And the 3 points in there are actual runs that we did where we measured F, and these are actual data points. So this is the actual performance curve that we don't know, right? We want to figure that one out. And so what Bayesian optimization does, it assumes a performance curve. It looks like this. And then you see the blue part above and below the curve, and that's the uncertainty, right? And you can see where we actually have a data point that the uncertainty is 0 because we know it's correct. And then the next point, this is overlaid with the actual curve. It's not really the same, but it doesn't matter because we will get to it. So Bayesian optimization then puts in basically a line with the best result you have, and then the blue part above the red line is the expected improvement curve at the bottom. And the higher that one is, that's the next parameter value you're going to try. So we're going to try the second one from the left. You can see we run the experiment, we get that result, we try that one, we get that result, we try the one on the left, get that result, and this one. And then you see that the curve that Bayesian optimization assumes slowly becomes the actual performance curve. And at the bottom, you see we've exhausted that space, so we don't have to run experiments down there anymore. So we go to the next one, which is the one on the right. That was not a good one, so we jump all the way to the left. We run this one. That was also worse than before. Then we go over there, and we find a better one, and then we continue over there, and we run all of them, and then we found our global optimum, because we exhausted all the space at the bottom, as you can see. And the curve is almost as it's supposed to be, but we found what we needed. This is basically what you would do as a human as well, right? But this just does it so much better and faster and cheaper. Okay, so we like Bayesian optimization because it's non-parametric, robust. Robust is important, extensible, well-tested on many types of real-world high-impact problems. So the thing is, we have to trust this algorithm, right? We have hundreds of microservices. Our goal for this project is to have Autotune always on in production, so that our services tune themselves constantly. So we don't have to actually monitor them or touch them to change the configuration. It would do it themselves. So we have to trust the algorithm to give us a result that's correct. And this one, as I said, it's been around for a very long time. I think I've read up on it once. Bayesian optimization was invented for oil drilling, to find out where to drill next, because drilling a hole in the ground is really expensive, so you want to be sure where to drill next. So these Bayesian optimization had a lot of applications, and so it's one we use because we trust it. And every now and then, I get asked, so why don't you use a more sophisticated machine learning algorithm? We don't need to, right? There's no data to learn on. Right? Every service is different. With different input data, it behaves differently. So there's nothing to learn, really. We just need to find out, we just need to measure performance and run it in multiple different ways. All right, that was it. So let's go to the experiments. That's the interesting part. So what is Autotune? I call it a BOAS, and I try to get this hashtag trending at every conference, and it never works. It's a Bayesian optimization as a service. So that's kind of meant as a joke, obviously, but it's true. So inside Twitter, we have a service, a Bayesian optimization service running that multiple teams use, and we as well. So Autotune, and it's called Wet Lab. It's a company that we acquired a couple of years ago, and Wet Lab, the software package, is an enhancement of a framework called Spearmint. And Spearmint is still open source, so you can get it on GitHub if you wanted to. Wet Lab is just a little more enhanced than that, but we unfortunately can't open source Wet Lab because of some IP, so don't ask me. And then Autotune itself, you can think of it as a complex shell script. It's really not much more than that, because the only thing it needs to do is to start and stop a service, get F, and talk to the Bayesian optimization service. That's all it does. But as you can imagine, the devil is always in the details, so that's the hard part. To run, start, and stop, and get data from the data center with all the security in place and blah, 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 that's the hard part, actually. And we are running in Aurora on Mesos. I don't even know if you guys still remember that. Everyone's Docker and Kubernetes, so we're still on Mesos. So it's, it's highly specific to Twitter, the thing we do, but the plan is eventually to open source what we have. If we found a replacement for Wet Lab and a way to start and stop services for other container formats. Okay, so what is Graal? So Graal is a Java virtual machine just-in-time compiler. Who knows what a JIT compiler is? All the hands should be up. I explained it earlier, so no one's paying attention. Okay. So it's actively developed by Oracle Labs. There's an official OpenJDK project page, but the most, actually all of the work in the Graal project is done on GitHub. So if you want to give it a shot, go to GitHub. If you have a problem, file a PR there. It uses JVM CI, as I said earlier, and it's written in Java, and we talked about that too. The fact that it's written in Java is not very important for this talk, but if you are running OpenJDK, and OpenJDK has Graal in it since JDK 10. So as an experimental JIT compiler, you can turn it on with some command line flags. If you're doing it this way, you might want to watch this talk where I explain a little bit the differences between the existing JIT compilers in Hotspot and Graal. Because the difference is the existing JIT compilers are written in C++ and Graal is written in Java. They have slightly different behavior. And if you want to know about this, if you're using a Graal VM distribution, the story is slightly different because the Graal VM distribution, since the last 2 or 3 releases, I think, they are AOT compiling Graal and linking it into Hotspot. So all of the issues that I'm describing in this issues, they're not really issues, they're gone. So think about that. Okay, these are the parameters that I'm tuning. I picked 3 inlining related parameters. Who knows what inlining is? Right, a few people. So imagine you're writing code, right? And then you have a snippet of code that repeats every now and then. So what you are doing as a very good, highly paid software engineer, you are factoring that piece of code into a method, right? And then you call it for different places. That's perfect from a maintenance perspective. It's horrible from a performance perspective. So basically what the compiler does, it undoes what you did. It puts the code back. That's called inlining. And that's the most powerful optimization we have in a compiler. It's also sometimes people refer to it the mother of all optimizations. It's because it makes the view we have of the world bigger, right? We inline more, we see more what's going on. Compilers work on compiler graphs, right? We parse source code, whatever that source code is, in our case, Java bytecode, and we parse that code into a graph, and then we inline more, and the graph becomes bigger. And then we can apply more optimizations to it. For example, escape analysis, one that's very powerful when you have more, when you see more of your world. So I'm tuning 3 inlining related parameters. The first one is called trivial inlining size, and it has a default value of 10, and that means 10 nodes in the compiler graph, right? So if a compiler graph has 10 nodes, It's rather small, so we always inline, no matter what. And then maximum inlining size is the other end of the spectrum with a default value of 300. If it has more than 300 nodes, we don't inline it. And then the last one is called small compiled low-level graph size. It's also a default value of 300. The difference, it's very similar to the second one. The difference between the two, almost every compiler has different levels of graph representations. Most compilers like C1, C2, Graal, OpenJ9's compiler, they also do that. GCC, I think, has something very similar. They have a high-level intermediate representation and a low-level intermediate representation. So intermediate representation is basically compiler graphs. The difference between the high level and the low level is the high level is high and the low level is low. You understand? Okay. That's how I explain things. I get paid for doing this. So, just kidding. So the high level one is closer to the source language. Could be, I don't know, C++ or whatever. In our case, it's Java bytecode, right? So the nodes in the graph in the high-level intermediate representation look close to the actual bytecode instructions, while the low-level one is close to the actual architecture you're compiling for. In most cases, it's probably Intel x86 or something, but it could be ARM or PowerPC or anything, right? So that's the difference. Okay. So I have a presentation that's called Twitter's Quest for Holy Grail Runtime. It's basically the story of me working the first year at Twitter, how we started running services on Graal, and what were the things we found, which bugs did we find, and so on and so on. And we had a very substantial performance improvement just by switching over to Graal. One of the things I did during this talk is I did what I'd said earlier you shouldn't be doing. I was hand-tuning it. And the reason why I was doing this is because I wanted to see, can I tune the compiler and get better performance out of it as a precursor to doing it with machine learning. And I'm going to show you 2 slides of my previous talk now. So this is, we're looking at GC cycles here, right? And ignore a little bit the red and the green color, because when I created these slides, we thought JDK9 would be the next JDK. We all know that didn't happen. So I'm comparing blue is C2. Oh, I haven't talked about C1 and C2 yet. Who knows what C1 and C2 are? Right, few people. So Hotspot has 2 JIT compilers. One is called C1 or client compiler, and the other one is called C2 or server compiler. You might have heard the client and server before, because we used to use -client -server back many years ago. The difference between the two is C1 is, its purpose is it's a high throughput compiler. So remember when I said we're interpreting code and that's very slow? C1 compiles quickly, doesn't do a lot of optimizations, does a little bit of inlining and other things just to get away from interpreting code, and then we run on native code. And C2 is a highly optimizing compiler. It uses all the optimization techniques there are in the world and tries to produce the best code it can. It takes a little bit longer to do that, but we're already running on compiled code from C1, so it's not that bad. Okay, C1 and C2. So we're looking at C2 here in blue or red, and then orange or green is Graal. And you can see we reduce GC cycles, it's not that much, by about 2 a little bit percent and 2 and something percent here. And the thing in the parentheses is what I got out of it by hand tuning the 3 parameters you just saw. So I got another 1.5% out of it, which I thought was pretty cool. This is more important here, it's user CPU time. So the number one important thing is here, just by running the tweet service, this is the tweet service, I haven't mentioned this yet. So the tweet service is the service that reads and writes tweets. Just by running it on Graal instead of C2, we save 11% of CPU utilization. It's ridiculous, right? If you ever worked on a compiler on some optimization stuff, you're happy when you get 1 or 2%. Well, it's almost like a lottery win. So 11 is a lot. And then by hand tuning, I got another 2% out of it, which I thought is pretty cool. I mean, 2% for 3 hours on a Friday afternoon. I was very happy, very proud of myself. Probably had a beer that night. But you will see that Autotune will kick my ass. Okay, so let's quickly talk about ranges. I gave my parameters value ranges. And the reason I did this, because you don't have to, right? You've seen how Bayesian optimization works. You could say 0 to 1,000 or whatever, right? It would figure it out by itself. The reason why I gave it ranges is basically for the presentation, because I needed it to finish in a certain amount of time. And if the space is too big, it would take too long. And I wanted to fit it on one slide. So this is for the presentation, basically. Test setup is very important. If you're doing performance evaluation and you're expecting only single-digit percentage improvements, you need dedicated machines. If you don't have dedicated machines, the only thing you are measuring is noise. If you run in the data center, or even worse, in the cloud that's not yours, you cannot even control what else is running on your machine. And then the noisy neighbors will completely destroy everything you're measuring. So if you want to do something like this, use dedicated machines. I use dedicated machines for this. For every configuration I had its own machine. And all instances receive the exact same requests. In the case of the tweet service, tweet requests. This is very important. It's not only the same number of requests, it's the exact same request. And the reason why this is important is because a tweet could be 1 character long or 280. And the memory allocation pattern for the two would be very different. But we want to compare apples to apples, so this is important. This version of JVM CI and Graal, it's not important. Default tiered C1 Graal setup, so basically I haven't talked about tier compilation yet. Who knows what tier compilation is? Okay, not a lot of people. So remember when I talked about C1 and C2, that we have 2 compilers in Hotspot? Basically the way we execute code is we interpret it first, slowly, then we compile with C1, and we compile it in a way that we compile in additional code that collects profiling information while we are running. And then we run on the compiled code for a while, and then after a certain number of iterations or whatever, we collect, for example, how often was a method called, how often was a loop executed, which if-else branches did we take, what types did we see at call sites, all these things. And after a while, we recompile with C2 and use all this profiling information to produce the best code we can. And we're stepping through the tiers, interpreted C1, C2, so that's tiered compilation. And basically the way we run Hotspot at Twitter is we replace C2 in a tier compilation setup with Graal. We are still using C1, but our top tier compiler is Graal. So this is what we're doing. Experiment 1, the tweet service, my favorite service. It's a Finagle thrift service. I don't know if people heard of Finagle. It's an extensible RPC system for the JVM used to construct high concurrency servers. I have no idea what it is. Literally, I have no idea, but I don't have to know. The only thing that's important to me is here at the bottom left, it's 92% of Scala code. So most Twitter services are written in Scala, and Scala is a language just by design, maybe I shouldn't say design, but by design, Scala produces a lot of temporary objects. And Graal has an optimization, C2 has that too, it's called escape analysis. I mentioned it earlier a little bit. And escape analysis, I'm not going into detail exactly how it works, but it can get rid of object allocations if the compiler can prove you don't need them, right? And the escape analysis implementation in Graal is better than in C2, and so it's able to eliminate more object allocations, which reduces memory pressure, which reduces how often we have to do a GC, and so on and so on. So that's why it's important that this is Scala. Our objective, what we are trying to tune, our F, right? You see here at the end, you can see user CPU time. So basically what I'm trying to do is to reduce user CPU time. And because reducing user CPU time means we can run the same service with less machines, which means less money, and so on and so on. So if you remember that Bayesian optimization always looks for a maxima, right? But we want to reduce something, so since we all paid attention at university and math classes, we're all very good at math. So how are we solving this problem? 1 divided by. It's amazing. That's why we get paid so much money. This is our constraint. I'm only using one constraint. This is a little weak, I have to admit. I would have to use way more constraints. Every service owner has certain metrics where they can tell if the service is still all right and healthy or not. We should be using all of these, but I was too lazy and it was only for the presentation, so I didn't care too much. And I know the service really well, so the only constraint I'm using is, you can see it here in the middle, it's called throttled. If Mesos is throttling us, we're doing something very wrong. Usually in terms of we use too much CPU, something like this. So that's the only one I used. Okay, here we go. That's 24 hours of the tweet service. And this is only requests per second, so the only thing to see here is that the graph is the same, because all of them receive the exact same requests. We have in blue the experiment, and orange is the control. And then you see these slices, right? These are 30-minute evaluation runs. So every configuration I run for 30 minutes, which is not a very long time. But again, I know the service really well. I know in 30 minutes everything's being compiled. We reached a steady state, and we can actually measure what we want to measure. If we would be running this, as I said earlier, always on in production, 30 minutes probably not long enough, because we don't know every service, how it behaves, so it would be different. But for this one, it's fine. And this is kind of the result, right? So this is, we're looking at user CPU time, and then you can see every time the blue line is below the orange one, that's an improvement, because we're using less user CPU time to do the same thing. The spikes you're seeing is the restart of the instances. And most of these spikes are chit compilations. So if, for example, to give you an idea, for the tweet service, we do about 40,000 chit compilations. And most of them happen in the first 30 seconds or first minute. That's where we compile most of the things. And then what you get out of Autotune is a web page, basically, and it has a table, and it's sorted by objective, and the top entry is 1.0838. Which means that we reduced user CPU time by 8.4%. You remember? I had 2 when I had tuned it. 8 is 4 times as much. And if you remember the graph I showed you earlier, we switched to Graal, we saved 11% just by switching over. This is on top of it, plus 8. So we almost saved as much again by tuning it as we got out of it by default. And then we have an 8.1, a 6.4, a 6.4, a 5.8. So if we're assuming that the first 2 are outliers, maybe we can expect a 6.4-ish% improvement. That's what I would expect. If we look at the bottom of the table, it looks like that, and you can see that 3 evaluation runs actually violated the constraint. So we tuned it too far, it didn't behave anymore properly, it was not healthy, so it got kicked out. And then there's another thing we can look at. You see charts up there, so let's look at the charts. These charts take the charts with some grain of salt because we're tuning 3 parameters, and so we're exploring a 3-dimensional space, right? So every data point in that chart depends on 2 other values that are not the same. But we get at least an idea of if there is a trend or something. So obviously the default value for this was 10, and we can absolutely see a trend going up. And it probably tops out at 21, 22, or something like this. And our best result was actually 21. And then this one is maximum inlining size. It's kind of flattish. There's a slight tendency going up. We have, at the top right, we have 2 data points that are better. They might be outliers. They might be not. It could be that just these 2 configurations paired with the 2 other flags were just so much better than everything else. But I don't care. I don't really care. I don't have to interpret this. I just take the best I get, right? It's a black box. I don't care. And this is the last one, and it's very obvious, right? The performance curve here is very clear. The default value is 300, but it should be more 580 or something like this, or 600. All right. So what I did do next was I took the best result of the table you just saw and reran the tweet service for 24 hours. So I did a verification experiment. And I wanted to see if I run this thing for 24 hours, do we actually see the improvement that we saw in the Autotune experiment? So this is just requests per second, the same as before. Blue is C2, Graal is orange, and then Autotune is Graal with the values we found. So this is GC cycles, and by just running on Graal instead of C2 in this particular run, we reduced GC cycles by 3.4%, which might not seem a lot, but we are still doing the same amount of work, right? We just have 3.4% less GC cycles, and remember, GC cycles always affect your latencies. So if you have less of them, your latencies are better. And this is Autotune, and you can already see that it's roughly the same improvement. It's like a 3.5% improvement. So if we would be using Graal as default and not change any configuration parameters, it would be nice. 3.4%, I'll take it. But if we're tuning it, we get twice as much. So if we wouldn't be tuning, we would throw out a lot of money, up to a total about 7%. And this is the same data, just in a different graph. It's basically how much bytes do we allocate to process one tweet, and it correlates with the GC cycles, obviously, but maybe some people understand this better. Same thing, 3.5, 3.4, and up to a total of 7. It's just the same. It's also, I should point out that it's pretty flat over the day, right? So we allocate pretty much the same memory, however the tweet looks like. And this is user CPU time. As I said earlier, that's the one I care the most about because that's where the money is. And in this particular run, we use 12% less user CPU time for running the tweet service on Graal instead of C2. And this is Autotune, and we get another 6.2. And the interesting thing here is I expected it to be 6.4-ish, right? And it's 6.2. So it's pretty spot on except the outliers. So this is a total of 18%. We can run the tweet service, which has thousands and thousands of instances, with 18% less machines. It's a lot of money. I cannot tell you how much it is, but it's a lot. It's way more than I get paid, right? I don't know how much you get paid, but it's more than I get paid. So, as I said, reducing GC cycles especially reduces also latencies. So we're looking at P99 latencies here. And the reason why I'm only looking at 2 nines and not 3 or 4 nines is if you look at 3 or 4 nines, you only look at the longest GC cycle. If you look at 2 nines, you kind of see the real world. And it's 99% of the tweets anyway, so it's fine. There's obviously, Graal is obviously better than C2. Little difficult to tell how much it is. Autotune is better than Graal, we can see that too. To see exactly how much it is, what I did was I integrated over the 24 hours, which is that, and then we can see the improvement on the right, and it's this. So just by using Graal instead of C2, we reduce P99 latencies by 20%. Imagine. And then we tune it, another 8, to 28% better P99 latencies for getting a tweet. So it means if you would pull out your phone right now and read tweets on your timeline, you would get them 28% faster. And if you scrolled really fast, you could read 28% more tweets. And I would appreciate that because that brings the stock price up and so on, and I can retire soon and not do this stuff anymore. No, I like it. So I did another experiment with a service called Social Graph. And the reason I did this is because Social Graph is also a finagle thrift service. A lot of our services are basically using the same stack. It's finagle at the bottom, Netty at the bottom, and then finagle, and then some logic off the service itself on top. So most of the code is the same as for the tweet service, and I wanted to see how different services, different business logic can impact performance. And in this case, Social Graph is an abstraction for managing many-to-many relationships at Twitter. So it's basically who follows you and who are you following. That's what it's doing. All right. So you've seen that before, same objective. We're trying to reduce user CPU time. Same constraints. I was lazy. Don't get throttled. And here is the run. 24 hours. It's a different day, so the graph looks different. Same thing, 30-minute evaluation runs. Nothing new to tell here. That's the result. Obviously, there's some better. There are also some worse. And here's the table. So the best one we have is 7.6%. which is nice. Absolutely take it. Then there's another 7.6, a 7.2, a 6.8, and a 6.4. So let's apply what we've learned from the tweet service, and let's say the first two probably are outliers, so maybe we get a 7.2-ish% improvement. At least, let's hope so. The bottom of the table looks like that. We had one that violated the constraint. There are 3 running, ignore them, that was a bug. And then let's look at the charts. It's similar to the tweet service, maybe not as obvious. But the thing to point out is the best we have is also 23. So 21, 22, 23, that's probably, at least for the code we're using, probably that would be the value we should use. Slight tendency going up. The best result is around 400. Sure, why not? It could be just the combination with the other 2 values is so much better. And this one is not as clear as for the tweet service. The one thing to point out in this graph, I'm not sure if you paid attention to the ranges that I showed you earlier, but the range here goes to 650. So, and I think my best result is like 648 or something. So maybe the range was not big enough. If I would rerun this experiment with a bigger range or no range at all, I might get a better result. All right, verification experiment. Let's see what the real world looks like. So again, same colors, same configurations. The social graph service uses a different GC than the tweet service. In this case, we're looking at CMS, so we're looking at part news cycles here. And we only reduce GC cycles by 1.6%. Sure, it's just the logic of the service, right? If you cannot eliminate as many objects, you just can't. That's it. And then Autotune, that's very important, and you can already see it in the graph. It tunes twice as much out of the compiler as the compiler gives you by default. So if we wouldn't be tuning this one, we would be very stupid and throw away a lot of money. And up to a total of 5%. So 5% less GC cycle is already something that's very good. This is user CPU time, and it's 5.5% by just running on Graal instead of C2. Interesting to point out here maybe is the reduction in GC cycle was roughly half of the tweet service, and also the CPU reduction is roughly half of the tweet service. So the two, if you can eliminate more object allocations, your user CPU time is also affected. Because A, you don't have to allocate the object, and that makes your code much tighter and faster. Your compiler graphs get smaller, you can inline more, but most importantly, you don't have to garbage collect it. And garbage collection is a very compute-intense operation. This is Autotune, looks like that. And also very interesting is 7.8, it's more improvement through the auto-tuning than what we get by default, up to a total of 13. So that's pretty good. I'll absolutely take it. Do we have any questions? Everyone in here, yeah, we have maybe 2-ish. Everyone in here should have this one question. Did anyone have that question? I'm usually very bad now. Okay, well, we'll get to your real question later. Because I'm talking a lot about Graal and how cool Graal is and how much we are saving, but remember this is actually an Autotune talk, right? So it would be very interesting, and yeah, of course I did, right? I couldn't come up here and say, Autotune works great with Graal, but it doesn't do anything for C2. So I wanted to see how well can Autotune tune C2, because C2 has been around for a very, very long time, and it's a highly finely tuned machine, so it would be interesting if we can get something out of this one. So which parameters did I tune for C2, because they're obviously different? I tried to find 3 parameters that are very similar to the ones we tuned for Graal. And the first one is called max inline level, and Graal doesn't have that. So max inline level is basically how deep inlining goes. How many levels of calls are we inlining? And at 9 it stops. Like it's a hard stop. There's no way to get around it except changing that flag. We picked 9 15 years ago, maybe. So code today is very different than 15 years ago, right? Everyone's using 1,000 of frameworks because it's so cool to download them from GitHub, and then framework A is calling framework B and calling framework C, you never end up at the code that you actually wrote. So this affects performance a lot. Then we have max inline size, which is basically the same as the first parameter for Graal. And 35 here is in bytecode size. So remember, for Graal, it was nodes in the compiler graph, but this one is bytecode size, how big the method is in the class file. If you ever had code, production code, and a small method, maybe performance-sensitive method, and you added assert statements to that method, and suddenly your performance went to shit, it's because of this guy. Because if you add assert statements in Java, it shows up in the bytecode. But C2 doesn't discount for assert statements. It's very embarrassing. I know we never got around to fix it. I'm very sorry. Use Graal instead. Inline small code is a very odd one. And the default value is 2,000 and 2,000 of native code. So the rationale behind it, I wasn't there when the flag was introduced. I think the rationale behind it is if you want to inline a method and you've already compiled it before and it's bigger than 2,000 bytes, you probably don't want to inline it because it's too big. It's kind of weird, but because sometimes even when you inline a big method, it can help collapse your compiler graph that you already have. So yeah, sure, I kind of understand where this is coming from. So it's odd, but we're tuning it anyway. So let's see what it does. Same thing, I gave it some ranges to have it finish in like 24 hours and get some decent results. And here's the run. Request per second, this is again the tweet service running on C2, and 30-minute evaluation runs. Really nothing new to see here. This is the result. So the best one we have is 5.1. Which is pretty good, right? I mean, 5% for a compiler as old and highly finely tuned as C2, that's pretty good. Then we have a 3.8, a 3.5, a 3.3, and a 3. So if we assume the first one is an outlier, we might be able to get a 3.5% improvement. That's what I would guess. Bottom of the table looks like this. Nothing much to see here, no constraint was violated, and then the charts look like that. Very obvious, right? I mean, everyone can see how this parameter affects performance, and that's the inline depth that I was talking about. Default is 9. I'm arguing it should be 16, 17, or 18 for all the code out there, right? If you're running the JVM today, I'm pretty sure you're running on C2. If you want to play around with performance a little bit, just bump that flag up to 18. And see what it does. This one surprised me a lot because it's basically, if you remember, similar to the first parameter we tuned for Graal, where there was a clear tendency going up in terms of performance, but this one is just flat, right? It doesn't seem to affect performance at all, which is interesting to me because it depends on the implementation of the compiler itself if a variable like this would affect performance or not. So I was really surprised. Was not surprised by this at all. That's the weird one with the 2,000 bytes. I didn't think it would do a lot. Yeah, maybe there's a slight tendency, but not really. So it doesn't really affect performance. All right, that was it now. So the summary of all of my talks that I'm doing is very long and very complex. It's that. And it's basically how you turn on Graal in OpenJDK. As I said earlier, it's in OpenJDK since 10. So if you are on 11, anyone running 11 in production? 1.5. He wasn't sure. Oh, well, so, okay, but you're getting there. So if you're running on 11, it's very easy to try Graal, because the only thing you have to do is add these parameters, and then you're running on Graal, and there's no binary incompatibility or anything. You just run on a different compiler. It's the same as running a different GC, right? There's nothing you have to do. Flip the switch and then measure whatever you can measure. I would be very interested if you could try this at your company or at home with your pet project or something, what your experiences are. If it runs better for you, excellent. I'm very happy about it. let us know, tweet about it, or post it on Facebook or Instagram, whatever we want to do. Send me a snap, right? That's cool these days. If it crashes for you, that would be perfect. Because if it crashes for you, that means you found a bug. And if you find a bug, then we don't find it, and then Twitter is not down, and my life's so much better, and I can be happy. If it runs worse for you, whatever worse means, slower, or let us know as well. Especially, the Graal team, file a bug on GitHub or something. It might be difficult if it's code from your company because it might be proprietary, you might not be able to share it, but maybe you can extract the test case or explain the situation, because we would at least be on par with C2 performance-wise, right? The thing, if you're running Java, right, we are doing a lot of Scala, and the improvements are so big because of what I said earlier, because Scala is creating all these temporary objects that we can eliminate. With Java, it's slightly different. So if you're running Java code on Graal, I say it's always like a 50-50 chance if it's better or worse. Because Java has been around so long, and C2 has been around so long, and C2, and I worked at Sun and Oracle on C2, not a single day or single hour or a single minute did we ever optimize for any other language than Java. Never. So C2 is highly optimized for Java code. But most importantly, the Java code you wrote is optimized for C2. Because you wrote it in a way that you got the most performance out of C2, right? It's very difficult for new compiler technology to come in and be better everywhere. So, but if you have an issue, let us know. We would be very interested. And I think that was it, really. Thank you very much. And I'm sure the two questions are still around. Yes? There was another question here. Did you have a question too? No? Over there.
I'm sure it depends on many things, like the priors, like the optimization functions, like the number of parameters that you fit. But for these results, for how long did you had to wait for the optimization to give you something useful?
Right.
I'm asking just as an impression, for how long do we need to wait for this to work?
Yes.
Is it hours, days?
Yeah, so it absolutely depends on how many parameters you want to tune, right? If I tune 100 parameters, we have to explore 100 dimensionals. That will take longer, obviously. 24 hours, right? That all you saw on the slide was exactly what I did. I didn't run it any longer. I showed you exactly how I ran it. I could run it for 2 days or 3 days. I don't think I would get a better result. So it depends, yes, as you said, on the number of parameters. It also depends on the service, right? How quickly do you get to a steady state? If the service takes 3 hours to get to a steady state, it will take longer. So there's a lot of parameters that would affect that, yeah. Yes? There are trade-offs using Graal instead of C2. Not really, no. So there is what I said earlier when I said I have this talk that's called How to Use the New JVM Check Compiler in Real Life. So the reason why I did this presentation is, and I said it earlier, I'm not sure if you remember, if you're using OpenJDK, you still kind of have to know about it. I don't have to say worry about it, but you should know about it. Because Graal is not AOT compiled. So basically, when you run, Graal, the compiler, needs to compile itself. Right? It's a meta-circular approach. So that takes a little bit of time, but it's not a lot. In our case, our services, they're not too big. They take about, let's say, between 10 and 15 seconds to start up a tweet service or something. It adds about 1 second of startup. So the other thing you should know is, since Graal is written in Java and C2 is written in C++, the memory allocation is different. right? C++ allocates memory with malloc on the native heap, while Graal allocates on the Java heap. Something you should know, especially when you run benchmarks or something and look at GC cycles or how much memory was allocated. And I've had someone do this from a very well-known company, so it happens. These are the only things you should know. If you want to try Graal on Java 8, right, which most people probably would do, there's only one downloadable binary you can use, which is the Graal VM distribution. And that one, as I said, AOT compiles Graal. So the problems I just described don't exist anymore, because memory allocation doesn't happen on the Java heap anymore, and it's being AOT compiled, so the compilation overhead goes away as well. So no. Besides that it could run slower, right? But it's for you to figure out. Most of the time it's faster. If you run Scala code, I give you a 99% guarantee that it will be better. With Java, you have to try. Questions? Don't be shy. It's Halloween. All right, cool. Thank you very much.